you like WebEx. Yeah, I do love WebEx. I think WebEx works really well. Zoom also works really well. From my understanding, Zoom allow you to do a lot of like backend changes. So it's more open in a sense that you can modify it in the way you want. But in any case, right? So let's look at how we can improve the GPU, right? How else we can do to make it better in the hardware, right? So this is just some of my research excerpt. There are many other works that looks into branch divergence as well. These are on the reading list, on the recommendation list, on the course website. Please definitely, if you're interested, check those out. Those are really important. What I do is I take into account of the memory divergence. It's two different research problem. But basically what I do is I zoom back into this particular question, right? And say, hey, we have a cache. And the cache here is being used only, is there for a reason, is only to filter out DRAM accesses. So instead of sending 8 DRAM accesses, you send 5. Which is awesome, to be honest. You reduce the off-chip bandwidth by a lot, right? But it's not fully the benefit of the cache, right? So what we found is sometimes when you run a GPU, you have the warp of these and these type. The first type that has a lot of cache hit threads, we call this a mostly hit warp. And the type that has most of the time is just cache misses, we call it mostly miss warp. And as you can see here, the two types will stall. It will wait for the same amount of time because it has to wait for the solar sky, right? If you imagine you have to run a marathon and you have to wait for me, I'm the slowest guy, and you have to wait for me, you'll be like, why, right? Same story. You have to wait for the slowest guy. But in the ideal case, right? In the ideal case, can we regroup them somehow? Not regroup or reshuffle or somehow do something with these warps so that, first of all, can I make room in the cache so that I can convert the mostly hit into our hit? And to actually make room, right? I mean, I don't care about that one screen box in the mostly miss warp. Most of them are missed, right? If I try to cache them, it's not gonna be any benefits. So I will just deprioritize them so that they become a mess to make more room in the cache. So that's our first goal. This way, we can reduce the stall time of the mostly hit because they're now all hitting in the cache, right? And to do that, we observe one more thing, that if you profile application and pick a warp at random, over time on the x-axis, you will see the hit ratio on the y-axis here is defined by how many threads are hitting versus missing inside the warp, right? You will see that they tends to stay in the same trend. If most of the time it hit, it would most of the time hit in the warp. If most of them are missing, well, they'll stay there, right? It doesn't go up by much. So you can use this observation to say, hey, there are different classes of warp. And if we can identify them, we can use a different strategy to basically prioritize the mostly hit and deprioritize the mostly miss. All right. Now, with this, right, we actually do one more optimization that looks in the L2 cache banks. Basically, the L2 cache works kind of like similar to DRAM, where you have bank L2 cache, right? But here's the thing. It's a GPU. GPU runs a lot of things in parallel. When I'm stuck on the load and store, I don't send one memory access. I don't send 4 memory access. I send a ton of memory accesses. By a ton mean more than 10. So these banks will be queued up. The buffer is going to get full, right? So when you have to queue up like this, most of the time you're spending is not spending at the bank. You're spending at the queue. You're waiting in line to be serviced. So we found that close to half of every single request has to wait actually more than 20 GPU cycle. 20 GPU cycles is really high. This is basically at least 2 or 3x the normal access time of a CPU cache. Right? So with this, we found that, hey, there's more thing we can do. If these are mostly misswap or all miss, just bypass them. There's no need to actually go to the cache because you're not going to benefit from it. So you reduce the cache queuing latency and the cache contention this way, right? So our proposal is called MEDIC, or memory divergence correction. First profile and look at the warp type. And based on that, we have the bypassing logic that if you're in a mostly miss or all miss, you bypass the cache. No need to queue up in the cache. This gives you two benefits. First, the mostly miss and all miss does not have to wait in line in the cache. Second, there are fewer people in the cache, so the line is smaller. So everyone benefit from it. So the second thing is we will insert, when you have a data into the cache, we will insert by deprioritizing the mostly miss and all miss, put them in the LRU. Only case that they're going to stay there is you have reuse right away. So if it's a popular address, it will stay there. If it's not the popular address, it will get kicked out right away. For other type, MIU like normal, so it stays there for longer. Now, to actually accelerate the all hit and mostly hit, you have to kill inside DRAM, saying if you are from the mostly hit or all hit, you go into the high priority queue. Why does this work? The high priority queue always is being prioritized over the low priority queue, but because these are mostly hit, they don't send a lot of DRAM requests. They just send 1 or 2. So these 1 or 2 requests get serviced really quickly. It doesn't really interfere. It doesn't really slow down the rest of the accesses because it's only 1 or 2 requests. The rest go to the low priority queue, right? So with that, right, we can get, comparing to the baseline that do nothing, the CPU state of the art, the GPU state of the art, we gain on average about 21.8%. And as you can see here, you see that it's effective for most of these workload category, except for a few. You can see that it's actually not that effective in some. For example, in this 3 scenario, right? 3 scenario here, we dig deeper and found that the reason why that's the case is because in that case, most of the warp are mostly missed. So we try to deprioritize them, so that actually slowing things down. All right, comparing to the state of the art baseline. So that's our conclusion, right? So this is a paper presented in 2015. It's actually now it's close to 8 years. By now the GPU kind of improved a lot comparing back in the day. But you can see how the concept can be applied to like addressing memory divergence. Around the year, I would say 2010 to I would say 2012, in fact, to around 2016, there's a lot of work that addressed memory divergence, branch divergence, and now there are actually now more architecture paper that kind of fundamentally change the way GPU should work, including things like oversubscription, right? So that kind of where we are leading into in terms of the topic we're going to talk about today, right? With the GPU, you mount the GPU. You basically, when you install the GPU on your computer, it's being put in the desktop as a slave to the CPU. You think about it. CPU becomes the host. It sends data to the GPU, it sends the compute kernel, and it tells when to run. The GPU just listen to that, take the command, execute the code, right? But yeah, that's all. Sorry about that. CPU has its own memory. It should be DDR5 by now. GPU also have GDDR6 or hybrid memory. No, high bandwidth memory, my bad. So it has its own DRAM. And these are connected through the slower PCIe or a fast NVLink, but still quite slow compared to just the bus to DRAM. All right. And the requirement is I cannot run anything on the GPU until the data is on the GPU side. I cannot run anything on a CPU if the data is not on the CPU side. And they share data. It does have this explicit memory management. You need to manually do the data copy. To get the performance, you need to minimize this data transfer. All right, you need to minimize this data transfer. And here's the problem. A typical operations, let's say you have a CPU and GPU, right? I'll first use CUDA-malloc. This allocate a free area on the GPU memory. Then when the data is ready, I'll do CUDA-memcopy, which basically copy the data that I want to compute into the GPU. Then I launch the kernel. When I launch the kernel, it processes the data from the green boxes to the results, which is red box, and copy back to the CPU. So a CPU has the result. And here's the operation. The arrow in the middle is long. It takes a lot of time to do copying back and forth and back and forth, right? So this is the long latency operation. In order to make to address the explicit memory management, let's say the programmer don't want to manually control everything. I can use the UVM or Unified Virtual Memory. Basically, this create the illusion that the two memory are under the same space. Then to do this, you would call CUDA-malloc manage, which would trigger UVM. And what UVM would do is it would automatically manage the data copy and do the demand paging for you, right? And this seems like a nice thing on paper, right? The benefit is on paper, this makes GPU much simpler. It's easier to program. But here's the problem. It's now managed by the hardware. Someone needs to tell when do I do the data copy. Someone has to magically say, copy the data right now. Here's what you do. Kick things out. This is done. Evict, copy, evict, prefetch. Everything here has to be somehow managed. And on top of that, let's say you want to share the GPU amongst many applications. You cannot really spatially share the GPU. Right? And this also applies to non-UVM solution as well, to be honest, but this lower the performance, right? And making UVM works is still an active research. It's not easy. Also, making GPU sharing works, also an active research. It's not easy to make it efficient. It's doable. You can do it, right? But it's not as efficient as you would wish it to be. The problem is coming from oversubscription. So we have unified virtual memory and demand paging. What you can end up with is, oh, sorry, I used too much memory. Let's say you want to run LLM, the large language model, on a GPU. One thing you know is it uses a lot of memory, right? Sometimes it doesn't fit. So if you somehow rely on UVM, the GPU will run. It can keep running. Whenever you need some data, you will demand page from the CPU side. But the problem is when you demand page, it degrades performance. Somehow it even crash the system, right? So to do this, to improve performance, you can hand tune, you can try to duplicate read-only data, so you have to copy back and forth and back and forth. But these involve manually moving the data, which kind of defeat the purpose of UVM. Then, if you share the GPU, you need to know your working set, how much memory you are actively using. Otherwise, someone else will use a lot of memory and you're giving page back. And when you run multiple VM or multiple containers, or even multiple applications on a GPU, you have no way to check, hey, for that application, how much memory is using? You have no idea. You have to guess. Right? And most of the time, if you're sharing the GPU, your guess will be wrong because there's no way to tell, right? So that's the need for demand paging management. That are application transparent. I don't want to change my application. So this is one of our earlier work on this topic. We look at multiple GPU application as shown here. I have a simple streaming access in 3D convolution. Basically, what it does is it streams through a bunch of addresses, and most of the overhead here is just waiting for eviction. Then you have the application LUD, where you have a bunch of kernels that has small working set, but they have data sharing. So you need to move data back and forth several times because the data here is being used again in cycle 200 and in cycle 350. And you have this thing like, for example, graph application are doing something like this. I have a large working set that touch a bunch of addresses, no trend at all. So you ended up trashing, right? There's not enough area in your GPU memory. And with this, we define them as regular application with and without data sharing and irregular application. For the first type, we just need to hide eviction latency. The idea is, well, I know I'm done with this data, kick them out of the GPU. So I have room to bring in new data. And that's it, right? The second type, I need to do the same thing as the first type, but also need to reduce data migration. And the last type, I need to reduce the working set. I need to make sure they touch fewer addresses that are unique addresses. To do this, we basically apply different techniques to mitigate different source of overhead. So our framework called ETC has a classifier to classify into different types and perform one of these, a few of these three things. Proactive eviction, make sure there's always room on the GPU to fetch new page in. Throttling means that I always try to slow the GPU down to make sure they touch fewer addresses. This would decrease the working set size. Capacity compression also do in-memory compression to decrease the working set size. And with the framework, none of these are working for our type. So for the first type, I just need to do proactive eviction. The second type, I need to do proactive eviction and in-memory compression. And the last type, we can't really rely on proactive eviction. We just do throttling to reduce the working set and compression to further reduce the working set. And with that, on y-axis here, you see performance of, here is the baseline where only 75% of my workload fit in the GPU memory. Basically, it doesn't fit. Here is a performance of ETC under this particular scenario. Then here's a baseline that only half of them fit in the GPU, and here's the performance with ETC. All right, it's not Ethereum Classic, I'm sorry, but it does basically stand for each of these mechanisms we apply. So we conclude that it's effective at identifying the type and correctly apply the policy to improve performance. All right, so this is called MEDIC, not MEDIC, sorry. This is called ETC. We present this in 2019. We does have a follow-up work in 2021 from the same team, Chen Li, who is basically at the time he moved to back to China as a professor, and we, along with his students, published another work follow-up on this particular topic on how to do the kernel scheduling to further reduce the overhead of UVM. On the software side, right, we also look into the multi-GPU. It is done in collaboration with folks from Korea, KAIST, and also Azure University and UNIS. Right. So what we do here is we look at multi-GPU. And in a multi-GPU, as you know it on your lab as well, right, at VISTEC, a few of you are doing this right now. I would run some workload on a few nodes and a different workload on a different node. And now this is connected through NVLink, which has a much higher bandwidth. And then when you have to talk to the CPU, this is done through the PCIe, they're slow. And one thing we notice is that some of these workloads use more memory than another. PageRank, for example, oversubscribed. It used too much memory, it doesn't fit in the GPU. But VGG and WCC is underutilizing the memory, it has room, right? So ideally, I want to kind of like sneak in so that PageRank can use the neighbor GPU memory. But here's the problem. When you have this, right, the UVM driver, which are in the CPU, will actually migrate the GPU memory from the oversubscribed node into the host memory. Data has to be swapped to the host memory. Right now, there's no support to fill into your neighbor memory. And this problem leads to a huge performance slowdown because migration is slow. Our solution presented at VISTEC ATC last year was to utilize the neighbor memory, to use them as a victim cache, basically, to cache these pages before you eventually evict them to the host, right? So that would try to allow the oversubscribing application on GPU 0, for example, in this case, to fill into GPU 1, GPU 2, and GPU 3. And the design goal is threefold. I want to hide the latency for both eviction and fetch. And then I want to make sure the programmer doesn't have to change a thing in the program. All right, so to do this, we pre-evict unused page ahead of time, and you do parallel data fetch for multiple off-shift links because you have a lot of bandwidth there. Then you do multi-path prefetching. We prefetch from both the host as well as the neighbor GPU, and we make this application transparent by only make sure we just modify the driver. And here's a key overall design, basically. You have, in this case, GPU 0 is oversubscribing. It fill into the GPU 1 memory in the victim cache area. And the way it works is you can pre-evict into this red box. Then if you need to kick things out again, it then being kicked to the host, right? Those are done in a slower manner. The faster manner is the NVLink path. So eviction happened there. Fetch, data fetch can happen from both GPU 1 and the host memory. So that way you have multi-path. You use both the PCIe and NVLink for your data. And this allows like a second tier of caching, if you will. Before evicting things to the host, you go to the victim cache first. If you have reused, you stay there. If you are done with using that data, then you evict to the host. And with that, we get about 3 times the performance improvement on average. All right. So that's the design of our hierarchical UVM. I want to kind of wrap it up because this is a little bit slightly different. It's like virtual memory on a GPU. We have 10 minutes. I'm not sure we have enough time. Let's actually try. So now you have a GPU core, right? Each of the core has a private and shared TOP and have a page table walker. This is basically the classic virtual memory as we know it, right? And if the data is not there, as you saw earlier, you have to now page to the CPU memory. The problem are in the red text. There's a limited TOP reach, high latency page walk, and high latency I/O. So it's a problem here. You can try to use larger page. So from say 4 kilobytes or 16 kilobytes, use 2 megabytes. You get a much better TOP reach because each entry is covering bigger area. The problem is you have to page things out of your GPU into 2 megabytes region. It takes more time than 4 kilobytes, right? So, but the 4 kilobytes has limited TOP reach. There's no one size fits all solution here. Our idea is, hey, let's enable huge page. Use both page size. The problem with huge page is if you have 2 applications and they malloc, they want to allocate the memory from app 1 and app 2, the green app and the blue app, right? And if they're going on like this, you can see on the right side of this figure, the small box is a small page, and the bigger box that I say large page frame, that's the area where you want to combine into a big page. You can combine them, but only for the first and the 5th large page. For the other 3, you cannot combine them because they are from 2 applications. If I combine them to the same page, the problem is they're mixing and there's no memory protection. Basically, you are now exposed to the other app. There's no memory protection. There's a big security issue. So you cannot combine these pages without moving the data. So if you want to move a bunch of 4 kilobyte pages, but that's a lot of overhead. On top of that, you need to search what page can be coalesced. Can I coalesce this? Can I coalesce that? A more desirable behavior with something like this. I have a guarantee that if I have allocation, they fall into the same page frame if they're from the same application. So this way, I don't mix the app, right? And this way, I can always assume that I can collect every single large page. But the problem is, I mean, the devil is always in the detail. How do I enable this, right? So in our paper, we have a way to kind of figure out how to collect them without moving the data. The paper is called Mosaic, proposed in 2017 at Micro 50. All right, so if you're interested, it's also on the reading list. If you want, you can check the paper out. And with this, we kind of follow up. So basically, this is the first work in the world, I think, as far as we are aware, to effectively enable multiple page size on the GPU. And then we look deeper into like, okay, if we have to do virtual memory, how bad can it be? It turns out to be around close to 40%, right? It's not ideal, and we want to figure out where is the performance overhead is, right? So if you look at this, basically what we found is that many warps in the GPU, when I have a TLB miss, when I have to do a page walk, not just one warp are stalling. Actually, on average, 8 of them are stalling. In some extreme cases, I see like 40 different warps are stalling from one page walk. Then in a GPU, you do a lot of things together in parallel. So you don't do one page walk. You do on average 8 of them. So there are more stall warp in this case. Basically, everything is not going, right? So our next paper kind of reduced this page walk overhead by applying multiple tricks throughout the hierarchy from the TLB, the data cache, and the scheduler to address the problem. This is called mask. So the paper kind of showed that the lazy page walk can hurt GPU performance, and you need to do something with this. All right, so that's kind of like a quick wrap about the GPU. The last thing I want to, let's do this on a network on chip lecture, basically the next lecture. But we'll talk about the idea called systolic array that kind of combine the network of processing elements and how to orchestrate data movement so that you can build things like a tensor processing unit or many accelerators if you see nowadays. All right. So that's a wrap for the lecture portion today. So we will pause, do a quick break. I'll be back at about 11:05. We will then do the Q&A on your own project. If you have any question about your project, if you have any question about the potential exam or the schedule, let me know. All right. So that's it. That's a wrap for today's lecture about VLIW and the GPU. All right. Thanks a lot.